Problem 45, jump game 2. In this problem, we are given an array of integers where each element inside the array at the position I represents the maximum size of a jump that you can make from this position. So 6 here means that we can jump at most to here, but we could also land in any of these other positions before it. But the maximum would be we could jump 6 spots to end right here. Now, with these conditions, the question is the following. If we start at the beginning of the array and our goal is to get to the end of the array, to the last element, what would be the minimum number of jumps that we can do this? We are promised that every test will contain at least one path, which takes you from the first element to the last element. So that's the problem. Let's now start thinking about this problem. I will try to suggest that we should probably traverse this array nums from left to right all the way and try to understand how many jumps, what is the minimum number of jumps to get to this element and then to this element and then to this element. And we will hope that every time we just understand what the minimum number of jumps are to get to all of these elements, then we could somehow calculate the minimum jumps to this element, the next element, and then to the next element, etc. So let's probably have another array, let's call it min jumps, right? And we'll try to basically, while traversing the original nums array from left to right, we'll try to populate this array somehow. And then once we get to the end of the min jumps array, whatever number ends up being here, that should be the answer, right? And we can return this number. So that's the idea. In terms of how we're going to populate min jumps, first we're going to examine this element. Well, we can start by populating this min jumps here with a 0 before we even start examining anything. So we can put 0 in here because we can get to the first element in 0 jumps because we don't need any jumps to get to the first element. So we can get 0, we can put 0 in min jumps in the beginning. Then we look at this 2 here. That 2 means those 2 elements can be reached in one more jump than this 0. So 0 plus 1 more, which is 1 jump, we can reach any of these 2 elements. Okay, now we're done with this element. Now we can process this element. And we see that element is reachable in 1 jump. So 1 more jump, that is 2, and we can get to the next 3 elements. So these 3 are reachable in 1 more jump, which is 2, 2, and 2. Now this 2 here is not better than this 1 that we already have. So if a better path is already, shorter path is already available, then we're not going to try to even store this 2 here. So we've processed this element, and now we can go to the next element. We see that this one is reachable in 1 jump, and that means next 6 elements, these 6 elements here, can be reachable in 1 more jump, which is 1 more than this, that is 2. So 2 jumps to all of these elements, right? Again, these 2 are not better than these 2 that we already have, so there is no need to write this because an alternative but equally good path is already available. So this is how we're going to continue. Then we're going to process this number and so on, right? Now, that will work. that will get some number k here, and when we're done, this number can be returned as we said, right? Now, how about the time complexity here? Now, in terms of this traversing the nums array from left to right, that seems to be fine. Time complexity here is O(n). And not only this is fine, this is absolutely necessary, the bare minimum time complexity that we must have here, because we have to deal with these elements, each of these elements at least once. So that's our like bare minimum, O(n). But in terms of how we're handling min jumps array, this may not be, this is clearly slower. So you can already see that we're going to touch these elements inside min jumps more than once, right? And if you try to think about the worst case about how more than once we're going to touch some of these elements here, think about a case when the nums array, all of those numbers here are pretty large. So from each of these elements, you can jump at least to the end of the array. So from each of them, you can jump to the end or beyond even, yeah? If that is the case, then think what our algorithm will do. So initially, this 0 will get in here, obviously. And then when we see this very large number here, right? Remember, this is a large number that takes us to the end of the array. So we will try to populate all of these elements inside min jump. And we'll probably try to write 1 in all of these elements. Then we move to the next element here, and this one will be also very large. So we will try to populate all of these elements with 2, and then we come here, and this is also very large, and then we'll have to populate all of these elements as well with number 3, and so on. And it's very clear that this is O(n) squared. Order of n squared, right? And the total will be basically, we'll get order of n squared total time complexity. Now, can this be improved upon? And I am suggesting that we can improve this definitely. Imagine the following. I mean, the whole problem of this O(n) squared comes from the fact that we might potentially deal with each of these elements inside the min jumps array more than once. So we might try to write a number here, and then we may try to write, or at least access this element another time. But if I ask a question, I mean, is this even necessary? Let's say we wrote a number inside min jump once. And if I were to somehow prove that this will never be improved upon ever again. So we might try to write number 2 or number 3 or number 5, but we'll never write them here. So there is no even need to ever even deal with this spot ever again. If I were to somehow prove that, then we could potentially, just intuitively so far, we'll prove this late in a minute. What we could do is kind of maintain a variable, let's call it edge, right? And this would point to the last element that we've already populated inside the min jumps array. And afterwards, if we have to populate some segment of min jumps again, instead of starting from here, we would always start from the next element after the edge. If I somehow succeed to prove the conjecture that I suggested, then we could do that. We could introduce this edge, and we could basically touch each element only once. And what that would mean is this overlapping kind of lines here would be replaced by something like this, right? So we would, so it would be something like this. So we touch some of these elements, and then we would
update these elements, then maybe we update nothing, and then we update this few, and then all of these. So again, this would look like on squared, on instead of on squared. Yeah, because again, we work with each of these elements only once, no overlapping lines anymore, right? That would be beautiful if I could only prove the conjecture that I just gave you, and I'll try to prove that in a second. Just get rid of everything. Now, in order to prove that, I'll start by proving first a small lemma, right? So if it is possible to get to any of the elements in k moves, then all of the previous elements should also be reachable at best in k moves. So maybe even fewer jumps, but sorry, not at best. At worst, it could be k moves. It cannot be that this is only reachable in, let's say, k plus 3. That would never happen. Yeah. So all of these elements before this would always be reachable, and reachable at worst in k moves, right? Let's prove that. Now let's say there is an element which is not reachable in k moves. So it could be never reachable, infinity moves, or just some, maybe k plus 1 moves is the best here. So in that case, what that means is, well, remember that this is reachable in k moves. That means there is some sort of path that takes us to here in k moves. Now, if that path ever actually lands in this element, and obviously that is not possible, right? Because then that would be less than k moves. That would be a path that takes us to this element in less than k moves. But if it doesn't, if we are jumping over this element at some point, then we could always cut this short, right? Because every number is the maximum size of the jump, but we don't have to do the maximum. We can just cut our jump short and land in here. And that would be at most k, because if this is the last arch of this one, then this is the kth jump. So we will cut it short, and in k jumps will be in this element. Or if there's not the last arch, right, then that means it will be even better for us. So this will be k minus 1 or 2 or something. Okay, so we've proved the first lemma that if there is number k here, so if this element is reachable in k jumps, then all of the previous elements are also reachable in k jumps. Now let's prove something else as well. Remember that lemma. Now let's do the following. Let's say we are running our algorithm. Now we're running our algorithm. And let's say we've reached this element here. So we have to process some ith element, which means we've already processed all of these, but we haven't processed any of these here. In terms of num jumps, our second array, so we've populated this one to some point, and that could be beyond our index I, right? So, and let's say this number points to somewhere here. So all of these elements now, okay, so let's say this element can be reached in k moves. That's what we've concluded by processing all of the previous elements. And by the way, this is not going to improve because all of the previous elements have now been processed. So if this says k, this k is not going to improve ever by processing any of the rest of the elements. Now, because this says k, we will try to write k plus 1 in all of these elements here. So if this is our edge somewhere, then we would try to write k plus 1 in all of these spots, right? And my conjecture is that these k plus 1 would be a waste of time to even try to see whether this can be written in here, because the number that is already here is at least as good as k plus 1 or even smaller. So that we can then start processing, start basically just writing to these spots only. Sorry, these spots. We're not writing to the nums array, right? We're writing to the num jumps array. Okay, so I have to show that none of these elements will have anything bigger than k plus 1 or even gaps. So all of these elements would be covered. Okay, let's again assume the contrary. Let's say one of these elements here has a bigger number. Let's say this is k plus 2, so bigger than k plus 1, which would be a disaster for us, because then we need to touch this, because if it says k plus 2 here, yeah, I probably shouldn't write it. I shouldn't write k plus 2 here. I should write k plus 2 here. So if this spot inside num jumps contains k plus 2, that's a disaster, because then we need to improve this and say k plus 1. Okay, if this contains k plus 2, what does that mean? So we can reach from one of these elements, because we've only processed these elements. From one of these elements, we can jump directly to here, and that would be our k plus 2 jump. So this element here has k plus 1, right? So if this element has k plus 1, that means this element is at best reachable in k plus 1 moves. Now, that is contrary to our lemma, because we know that this element here was reachable in k moves, is reachable in k moves. And then this element is reachable in k plus 1 moves. So, or at least it was at some point, but that would have never improved. So, because that would have, so when we updated, when we wrote this, we had already processed everything before it. So if we had k plus 1 at that point, this k plus 1 would never have decreased. This would never have improved. So this is still k plus 1. This is the final answer for this element. Impossible, because we have k here. According to our previous lemma, that is impossible. So what that means is we can basically have a rather efficient algorithm. Can we prove, by the way, that there can be no gaps? I mean, it should be the same, because gap means infinite number of jumps. It's just the skill whether I can actually formulate my proof in a way that in one proof I could capture both finite and infinite situations, because it's the same thing. Let's say this one is a gap, right? So this, we've written a number here, but we are unable to reach this. Now, because we've written a number, so right, of course, because if the edge is here, then this should already contain some number, because we know that if we can reach this element in some, again, because from our lemma, if this can be reached in some whatever k plus 3 or anything number of jumps, then this also can be reachable through the same number of jumps. And although this is kind of the final story and we haven't finished the processing of the entire array, this lemma still can be modified, that this, from whichever element this can be reachable by k plus 3, from the same element, you can reach this element here in at worst k plus 3. If you remember how we proved our lemma, I should probably have done it like that. So technically my lemma would be, if you can reach any element in k moves, then any of the previous elements can also be reached maximum in k moves, and without touching any of the other new elements, just simply using only those elements that were engaged by this path. Well, with obvious potential exception for the new element that we're now trying to reach. Okay, that all kind of makes sense, I hope. So the only thing that remains would be to try to actually write this whole thing. Yeah. Let's try to get back to our browser and try to write this. So what we said is we're going to create an array min jumps. Didn't we say that? And this would be what? Let's say a new array of number, nums length. So we need the same size of an array. And technically, I would need to fill it with plus infinity here. But because the way JavaScript works, we're going to just to make this faster, we could remove this. But let's keep it like this. So we should fill it with some sort of maximum integer. Depends on what language you're using. Int max for C++, but with JavaScript, we can just do plus infinity. And instantly, we can pre-populate min jumps 0 with 0, because we said that, right? If you remember. This is this 0 right here, right? Now we also need edge, right? We need edge. As soon as we populate anything in min jumps, we're going to instantly update edge to say, well, edge should be always pointing to this index, which already, the maximum index that we've written to, okay? Now we can go through our array. We probably don't need to go to the last element. So we don't need to process this element, actually, because if we process this element, we're never going to update this element that is of our interest. This will potentially be updating anything further, but there is nothing further, so we don't really need to touch this. So this is I is less than last element, strictly less than last element. Now, let's create a small constant. So we're going to basically, what we're going to do is do min jumps I plus 1. So min jumps I plus 1, that would be the number that we have to write, right? So if we are at this point, k is our min jumps. So we min jumps I is how many jumps, the minimum number of jumps required to get to this element. And then one more, this plus 1, means all of the future elements that are directly accessible from this spot can be reached in this number of jumps. I think that makes sense. Okay, so what we now have to do is actually write this number to all of these future elements, right? So we basically have to, if this is 4, so the next 4 elements, right? We have to write this k, but we can start from edge. If edge is pointing here, then we would start from edge plus 1, right? So let's say 4, let j equals edge plus 1, but it cannot be just edge plus 1 because, sorry, edge or I plus 1. Let me just max. So it's this. So it's edge plus 1 or I plus 1 in the maximum of those two, right? Because potentially edge plus 1 would always be at least as big. I think edge plus 1 would always be at least as big as I plus 1. Yeah, because if edge is not as big as I, that means we cannot reach this element, and we're promised that this will never be the case. So I don't have to do that. I can just say edge plus 1. I can say that. And then I can say, well, because just let me say, what are we going to be doing here? We will be populating min jumps j, and that would be equal to min jumps, sorry, that's not good. We have a naming conflict. It's not great that this doesn't really give me a better, as I type, there is no checking of my code, and that kind of keeps me half blind now. So min jumps j would equal to this min jump that we've just calculated. And obviously, at the same point, we're going to update edge and say that, well, we've just written, and because j is going to be bigger than edge, right? Then I can just always update edge to equal j. Now, we could take this outside of the loop, but I won't worry about this for now. Instead of doing this assignment every time we go through the loop, we could do it afterwards, but that would well, this is nicer. That would not give us better time complexity, and this always just ensures that every time I touch min jumps, I update edge, right? Now, the loop. So j starts from edge plus 1, but j maximum should be, first of all, it shouldn't fall out of the array, right? So it should be less than num's length, because num's length is the same as min jump's length. They have the same length. So, but let's write min jump's length. Even though they have the same length, it should make sense. So j should not fall out of this array, but it also should stay. J should be less or equal to what? I mean, it should be less or equal to nums I plus I, right? Because we're at the spot I, and we couldn't jump to I plus nums I. That would be the last spot that we could jump to. So it should be less or equal to I plus nums I, correct? And then we need plus plus j. So with that, we covered mostly everything. Well, here I would return min jumps at -1. So the last element, right? Hopefully we haven't added anything beyond the last element, which is very easy to do in JavaScript by accident. So we could also terminate this. I mean, as soon as we reach element with index in here, because we know that as soon as we populate min jumps, so we could quit, right? So we could quit. We could say here, could I say and edge is also less than num's length, so that we can, as soon as edge reaches num's length, no, even when it just becomes, so let me see, if edge becomes num length -1, we should also quit. Yeah. And potentially this could be copied. That would be That would be unpleasant. Actually, that makes things really ugly. So should we just say if edge is more or equal to num's length minus 1, so if it reaches the last element, then break. And potentially the same thing can be done here, but I mean, that would not be, well, let's see. I mean, let's see what happens. This will just be minor improvement in terms of time. Okay, pretests have been passed. Let's try to now run the main tests. Okay, that means probably we've passed, which is 2 milliseconds, 5 milliseconds runtime. Okay, I mean, this is decent performance for TypeScript. We could rewrite this for C++, for example. But, well, I think this is fine. This is fine for TypeScript.